This is section 11.6, plane curves and parametric equations. We're going to begin by talking about what a plane curve is, parametric equations are, and how to graph a plane curve. Let's talk about a plane curve. Let f and g be functions of t over an interval. Then the set of points defined by f of t, g of t. So f of t is your x-coordinate. Another function of t called g of t is your y-coordinate. That is what you plot on this plane curve. Parametric equations. Parametric equations have what we call a parameter, and the independent variable is t for each of the functions. So both functions f of t and g of t are defined with parameter t. They are dependent on t. Now, to graph a plane curve, what we're going to do is we're going to create a table of points. Then we're going to choose arbitrary values of the parameter t, and then we'll find, so we're going to choose arbitrary values of t, and then we're going to find the values of x and y, and that's what we will plot, those values of x and y. And we will plot them in the order of increasing t. So as t increases, that's how we will connect our points with that curve. We'll use arrows to indicate direction or orientation. You can call that direction also of the curve. And this is the direction of the path for increasing values of t. Very important. Okay, let's start with number 1. We are going to be plotting points over the interval from -3 to 9. And we are not including -3. And we are including 9. Okay? So we have x equals t over 3 and y equals t minus 4. So you can see that x is a function of t, and that's 1/3 t, and y is also a function of t, and that's t minus 4. I don't know if that helps, but I thought I might write it like that. So x and y are functions of t. Let's go ahead and make a table. So we'll have t, and then we're going to have increasing values of t on this interval, and we will then compute x and y with that t value. I think I made those big enough. Maybe I should go ahead and make them a little bit longer, make that table a little bit bigger. Okay, so let's just start with -3, but keep in mind we do not want to include that point, so that's going to be open. And then, of course, the rest will be closed. Okay, then let's just go ahead and choose 0, maybe 3, 6, and we can stop at 9, and we are including 9. So when you plug t equal to -3, so you'll have x of -3, and that's -3 over 3. I'll go ahead and write that a little bit better. That's 1/3 times a -3. That's -3 divided by 3, and that's a -1. I'll do these first ones for you. Y of -3 is a -3 minus 4, and that's equal to a -7. You can pause the video if you'd like and finish those up. I'm going to go ahead and fill these in. All I have done and so forth is plugged each of these t values in. So this was when t was equal to -3. That's what these computations were. Okay? and then you could just go on and find the rest. So when t is 0, x was 0 and y was -4. When t is 3, x is 1 and y is -1. When t is 6, we get both x and y equal to 2. And when t is 9, x is equal to 3 and y is 5. So keep in mind, we are only plotting x and y. We are not plotting t. Both x and y are dependent on t. So let's go ahead and do that. Our first point would be -1, -7, and keep in mind that is an open point. And then we have 0, -4, 1, -1, 2, 2, and 3, 5. Now, this is a curve here that we can go ahead and just plot. Like that. I think that looks good. And let's use some arrows in the direction. So that means as t increases, this is what we have. So keep in mind, we do have an open point at t equal to -3, which is at the point -1, -7. Okay. Now let's talk about how to eliminate the parameter. Each one of these functions were dependent on the parameter t. How would we eliminate the parameter? Well, first someone gave us parametric equations. What we're going to do is solve for t or an expression involving t in one equation. Then we'll substitute that result into the other equation, and then we will go ahead and identify the restrictions on the domain, because now we will have a rectangular equation. So we'll start with parametric equations, and we'll end up with rectangular equations. Okay, let's give it a try. Let's start in number 2, eliminate the parameter t, and then sketch the curve. Okay, and we'll see what we have. So what I would like to first do is go ahead and divide both sides of this equation by 4. So I would have x over 4 equals e to the t. So now I'm going to go into the other equation, and everywhere there's an e to the t, I'm going to substitute an x over 4. So now I have y equals -3 times x over 4 plus 4. And now I can go ahead and solve that. That's y equals -3/4 x plus 4. So this is a linear equation. We have slope of -3/4, and we have a y-intercept of 4. So that gives us a 0.04 on the graph. And here we have a decision to make. Do we have an open or a closed? So are we open at 0,4 or are we closed? So let's take a look at what we have. If we go back to the original parametric equations, let's go ahead and take a look at this right here. As you see, x is equal to 4 times e to the t. E to the t is always positive. So 4 times any positive number is going to be positive. So x always has to be a positive number. So if we take this x has to be a positive number and place it right in there, we have that x has to be greater than 0. And we do need to include that. So that leads us to an open circle here, since x has to be greater than 0. Okay, so let's keep going. If we have a slope of -3/4, we're going to go down 3 and across 4. Down 3 and across 4. And now we can connect those points. And as you can see, as t increases, the graph will move in that direction. Okay, let's go ahead and take a look at number 3. Eliminate the parameter t, sketch the curve, and indicate the orientation. So the first thing we want to do is go ahead and solve directly for t this time. So this would be 8 in the denominator, divide both sides by 8. So we have x over 8. You could also say that that's 1/8 times x. So now we will have 1/8 x going in, being substituted in for t. So now we have y is equal to -6 times 1/8 x plus 4. And that's equal to -6 over 8 times x plus 4. And we end up with y equals -3/4 x plus 4. Now, let's take a look at that. This is a linear with slope of -3/4, and the y-intercept is b. So let's go ahead and take a look at the restrictions on the domain. There are no restrictions. So whatever t is, either positive or negative, it's going to make x not have any restrictions. Okay? So with no restrictions, we will need the complete line. So let's go ahead and plot a point. We'll use the y-intercept, then we'll go down 3, across 4, down 3, across 4, and now we are going to connect all of these points and have this complete line look like this. Now, as t increases, x is going to increase, as you can see here, right here. Okay? And so you could also think of it as x increases, look at that, as x gets larger, t is going to also get larger. So we know that our arrows, I shouldn't have had that there, but we know that our arrows and our direction is going in that way, in that manner. Okay, let's look at number 4. Eliminate the parameter t, sketch the curve, and indicate the orientation. We first want to note the restrictions here for x. When we have 3 cosine of t, the amplitude is 3. So we know that x is going to be between -3 and 3. The cosine is between -1 and 1. I shouldn't have said amplitude. And then when we multiply 3 times that, we now have our restriction on x. That is the same here for the sine, the -4 y will be between -4 and 4. The sine is the same way that the sine is restricted between -1 and 1. In fact, I could rewrite that about there. And this time we'll have 4 times -1 and 1, and that's why our restriction on y, on the range. Okay, we do have the t is between 0 and 2 pi, so we will only graph that from t equal to 0 to t equal to 2 pi. Okay, so now let's go ahead and take a look at the cosine of t, and we can see that the cosine of t is going to be x divided by 3. Whoops, I should have had a 3 here. And so the cosine of t is x divided by 3. And if we have y equals the sine of t, we have that the sine of t is equal to y divided by 4. Using what we already know, our identity that the cosine squared plus the sine squared of an angle is equal to 1, we will have the cosine of t, which is x over 3 squared, plus y over 4 squared is equal to 1. And that becomes x squared over 9 plus y squared over 4 equals 1. And you guessed it, we have an ellipse. And let's go ahead and plot that. So we have our major axis, -4 to 4, -3 to 3. And let's see if I can connect those. I think I did a circle. Let me try one more time. And I don't think that's going to work. It's okay. I think I can do a pretty good job. Okay, so we have an ellipse. Now, if we're starting at t equal to 0, the cosine, so we could just say we're starting at t equal to 0. And so x is equal to 3 times the cosine of 0, and that's 3 times 1, and that's 3. So our x coordinate is 3. So here's where we're going to begin, and we will move in this direction. But here is where we will start, right here. Whoops. Okay, you could also say that this was my initial point, and then travel in that direction. Okay. I think I made an error here. I think that should be a 16. There we go. Okay, now let's go the other way. Now let's try to write parametric equations to represent a curve. So we're given y equals 5x minus 2. And in part A, we have x equals 2/5 t. So we will substitute 2/5 t in for x. So we have y equals 5 times 2/5 t minus 2. And of course those 5's cancel. And we will have 2t minus 2. So now we could say that x equals 2/5 t and y equals 2t minus 2. And here are our parametric equations. Those are our parametric equations. Let's try another one. We are going to substitute 2t minus 5 in for x. So we have y equals 5 times 2t plus 5. And don't forget about that. 2t plus 5. And then we have a minus 2. And so we have y equals 10t plus 25 minus 2. And then we have 10t plus 23. So now we have x equals 2t plus 5, and we have y equals 10t plus 23. Both of these are parametric equations with the parameter t. Okay, now we're going to write parametric equations for t given the graph. And there can be multiple solutions. What I'd like to do is first grab that y-intercept. B is equal to 4. So that point 0, 4 is on the graph. Also, let's note that this slope is equal to 1. Up 1 over 1, up 1 over 1. So we have slope equal to 1. And with that, we have y minus 4 equals the slope, x minus 0. Or you can have y equals x plus 4. So if we let x equal t, then we will have y equal to t plus 4. And there are several solutions. Keep in mind there may be multiple solutions. This is one of many solutions. Okay, now let's talk about modeling with parametric equations. What we want to do is make sure we let t be greater than or equal to 0 when we're dealing with time and motion along a plane curve. Okay, so if an object is in motion, we don't want negative time. And then we do want to make sure we let x sub 0 and y sub 0 represent the initial position at time 0. Okay? So uniform linear motion, we have these two parametric equations. X equals the initial position, x coordinate plus at, y equals that initial y coordinate, initial position in terms of y, plus b times t. The values of A and B are the horizontal and vertical components of velocity. Projectile motion. We will be using x equals v sub 0 cosine of theta times t plus x sub 0. Keep in mind that v sub 0 is the initial speed. That sub 0 is initial, and then v is, of course, our speed. It is the magnitude of our initial velocity. Theta is the angle of launch, and that's relative to the horizontal. Y is going to be equal to negative 1/2 gt squared plus v sub 0 times sine of theta times t plus y sub 0. Now keep in mind g is the acceleration due to gravity, and we will be using 32 feet per second squared or 9.8 meters per second squared, depending on your units. And that's on the surface of the Earth. Keep in mind we're going to neglect air resistance. So let's look at number 7. An object undergoes uniform linear motion. So we'll be using these equations right here on a straight path from point A, which is 3/8, to point B, which is 6/10, in 3 seconds. Write parametric equations over an interval that describes the motion along the path. Okay, so let's go ahead. Our initial position is 3 for x sub 0, and of course our initial position in terms of y, or our y coordinate, is 8. This is when t is equal to 3. Okay, so now let's go ahead and find out what A is. A is equal to 6 minus 3 all over 3, and that's equal to 1. And B is equal to 10 minus 8 all over 3, which is equal to 2/3. Where would we get that? If you can see right here, solving this for t, we have x minus x sub 0 all over A. Excuse me, you could solve it for that, but we're going to solve that for t. A is equal to x minus x sub 0 all divided by t. Finally got that right. And B equals y minus y sub 0 all over t. And that's where we found these. So maybe I'll go ahead and switch these just to have a little bit more detail. This is going to be x minus x sub 0 all over t. And that's equal to 6 minus 3 all over 3. So t is equal to 3. This is x sub 0, y sub 0. And you could call this xy, that point B. Okay, I'll do that here. We have y minus y sub 0 over t, and that's 10 minus 8 divided by 3, and we come up with 2/3. Okay, so with that, we now have x is equal to x sub 0 plus at, so x is equal to 3, which was x sub 0, plus a is 1 times t. So x is equal to 3 plus t. Let's take a look at y. Y is equal to y sub 0 plus bt, and y sub 0 was 8 plus b we found to be 2/3 times t. And those are our parametric equations. Let's look at our last problem in this section, and it's another application problem. And a ball is thrown from a height of 5 feet. Well, almost immediately I am drawn to wanting to make a quick sketch. So I'm going to start here at 5 feet, and I'm going to throw a ball, and that ball is going to hit the ground. Let's keep reading. So a ball is thrown from a height of 5 feet at a speed of 80 feet per second. So that speed is 80 feet per second. So that's the initial velocity is 80. Now, our initial height is 5. And you should be able to see, let me rewrite that. You should be able to see that x sub 0 is equal to 0 because this point here is 0, 5. Okay, let's keep reading. At an angle of 60 degrees from the horizontal. So we see that theta is equal to 60 degrees. We'll jump right in and write that x is equal to, and keep in mind we have v sub 0 times the cosine of theta all times t plus x sub 0. Y is going to be equal to negative 1/2 times gt squared plus, now we have this other component. I better bring all of this over. And let's continue. Sine of theta times t plus y sub 0. Let's go ahead and get these written down. And I could make this sketch just a little bit smaller and maybe move it over here just so that we have some room. And we have x is equal to 80 times the cosine of 60 degrees times t plus 0. And we actually have x equal to 80 times 1/2 all times t. So x is equal to 40t. Let's do the same thing for y. Y is equal to negative 1/2. Since our units are in feet and seconds, we will use gravity as 32 feet per second squared times t squared plus 80 multiplied by the sine of 60 degrees times t plus 5. And now let's continue simplifying. I have a negative 16t squared plus 80 times the square root of 3 over 2 times t plus 5. So we have negative 16t squared plus 40 root 3 times t plus 5. So, as you can see, we have two parametric equations, x in terms of t and y in terms of t. Now, the question was, determine when the ball hits the ground. So at the ground, so when the ball hits the ground, y is equal to 0. So let's go ahead and plug in 0 for y. So we have 0 equals negative 16t squared plus 40 root 3 times t plus 5. Now, as you can see here in using the quadratic formula, a is 16, b is 40 root 3, and c is 5. So t is the opposite of b, plus or minus the square root of b squared, and we're going to put all of this in our calculator, minus 4 times negative 16 times 5, all over 2 times negative 16. And when I put that in my calculator, let me move that a little bit over to the left so I can continue. I got approximately, and I did the plus or minus, a negative 0.07 and a 4.4. Of course, we have to throw out the negative value, so we come up with, therefore, 4.4 seconds later. That's when the ball hits the ground, at 4.4 seconds. And that concludes this section.